A video overview of the physics derivation graph. This is the current capabilities as of the April 10th, April, somewhere in April, April 7th.
Don't start over.
All right, no. All right, so I'm currently in the version 7 directory, and so I'm gonna run my Docker Compose file. When I run my Docker Compose, it's going to initiate a Flask container as well as a Redis container, Nginx, and gUnicorn. And the Redis database is connected to Flask, but it's currently not in use for anything. I'm actually using a plain text JSON file to store all my data. So that will be a problem in the sense of if I have multiple users, it won't work out very well. So I'm going to, so this is basically showing that Redis started, then Flask started, and I should hopefully be able to get to a web interface by typing in localhost. And if I go there, I get this web page. I'm going to open up the editor in a new tab because it usually times out. And I'm able to see sort of an overview of the project as well as documentation for users on this page, and then documentation for developers. So let's open those up. Now the reason that the editor page times out is because it opens up a bunch of image generation tasks, and those take about 40 seconds. And so the page times out with a bad gateway. But then if I come back and try it again, it will work. So I'll demonstrate in a moment. So here I have user documentation. So it sort of walks through what a user should know about the physics derivation graph without getting to any of the sort of technical content. So a couple of comparisons with other projects, but basically just a very superficial overview. And then the documentation for developers, which has this cool sort of table of contents here, also has all the sort of technical details that you would need to know about the project if you're going to contribute. So it's much more in depth, give some example use cases. This is connected to MathJax, by the way, for the LaTeX display. So this looks to be what you'd expect out of LaTeX using MathJax. And then some citations. Okay, so let's now that the editor has loaded, let's see if we can pull it up again. All right, so now I'm in the physics derivation graph editor, and I have a set of choices. I can look at all the operators, which there are not very many. And I can go back to editor. The second time I click on it, it's much faster. If I click on symbols, I get all the symbols, not in an HTML table yet. I can go to list all the 309 expressions. This is a dynamically generated number here for my table. And then the HTML table here has all of the content, and I can sort it because the table is sortable. And then if I go down to the bottom of this table, I have the option to delete expressions and edit the LaTeX for an expression that exists. So I can choose which expression I want to edit and then revise the text for that. Okay, so that's the list all expressions. Similarly for the inference rules, it's also an HTML table with sortable columns here. And I see where a given inference rule is used. So if I wanted to figure out what is the most used, I would look at declare initial expression as the most commonly used inference rule. And there's 71 of those. And at the bottom of this page, oops, I can go and I can add an inference rule, delete an inference rule, rename, and edit. All right, let's go back to the editor. And if we look at the existing derivations, so for example, I have multiple derivations already loaded in. I can look at the graph viz for that. and I get back that there was an error in SymPy parsing, but I still get a D3GS graph that's interactive, a static graph viz, and then some tables. Alright, so let's look at the D3JS interface first. Here I can mouse over a given node, and then I can move it around, and it highlights what it is connected to. So this is a step, effectively. If I mouse over one of the inference rules, I see the steps. Now, one problem here that I haven't resolved yet is that I need arrows on my edges to indicate directionality. That doesn't exist yet, but it is interactive, and all the steps are sort of highlighted with the same, with different colors, whereas the expressions are all blue. And then lastly, I can sort of zoom in, zoom out, and so the PNG here is pretty well resolved. Alright, so that is the D3JS visualization, which is pretty, but sometimes hard to read, which is why there's also a static PNG, and the PNG has different colors and different node shapes for the different node types. So this is a feed, an inference rule, and an expression. So these are you've got the D3JS, the graph viz, and the third representation is this table. So the table, each row is a step in the derivation, and then if there weren't any SymPy errors, you'd have an indicator of whether or not the step was correct or not. Again, this table is sortable, so I can sort of select the sorting of columns, and then each of the LaTeX entries have their global ID linked. So if I click on that, it'll take me back to list all the expressions and then highlight which row I was on, and I can see where that was used. So if I go back to any of these other, I can see, like, was this expression used anywhere else? And the answer is no. Alright, so that's sort of like a quick overview, and then at the bottom, the last table I have is the list of expressions down here. At the bottom of each page, I have the rendering time in seconds, so we can see where that is. Let's go back to the editor. And let's look at another derivation. Let's say Maxwell field equation, or Maxwell electric field equation, and we can click on Generate PDF File. And what we get is a PDF with hyperlinked equations. So ideally, I could click on any of these, and it would bring me to that expression line. So these are all generated dynamically. And we can also get to that from the graph viz. If we look at the graph viz view first, that was also generated dynamically, and there was no SymPy errors, so hypothetically we should be able to see step validity. So there aren't any validations available for the math used here, but you can see that the analysis was run. Okay, and then I can get to the PDF from that view also. Alright, so let's go back and create a new expression, a new derivation. So I'm going to make a new derivation. We'll give it a name. And then we're going to declare an initial expression. And we'll set that expression as A equals B. And so now it populates that steps in the derivation here with one entry. And so I want to add another step. So I'm going to claim that the left-hand side equals the right-hand side. And my input LaTeX this time is the local ID. and I'm going to use that. And I got a complaint saying that A is not equal to B in fact. So this step is not valid. I'm going to add another step. Let's actually review the derivation first. So I declared an initial expression A equals B, and then I claimed that left-hand side equals right-hand side, and that failed. But let's go back and add another step. I'm going to declare a final expression. And here we'll say that the output ID is going to be used for, I'm going to use that. So that is my step now, and there's no validation available, so let's review the derivation. So I now have that I declared an initial expression A equals B, and then I claimed that it was left-hand side equals right-hand side, and also that I declared the final expression. Okay, so that is basically the quick overview of the derivation graph. There's lots of features to be added, but at this point, the concept hopefully is demonstrated.